Okay, starting section 8.1. Now, section 8.1 and section 8.2 kind of go hand in hand with each other. Section 8.1 is the law of sines, section 8.2 is the law of cosines, and both of those sections have to do with solving of triangles. Remember, we did that early on with right triangles, solving a triangle where you're looking for the measures of the angles, lengths of the sides. Well, what happens if our triangle is not a right triangle, if it doesn't have a right angle in it? And so that's what these two sections are going to deal with. All right, so solving triangles. All right, so again, solving a triangle means to find the lengths of all of the sides, measures of all of its angles. And back in section, that should be section 6.2, we solved right triangles. And we were able to solve those, using the sum of the acute angles of 90 degrees. I mean, we could still use that in our non-right triangles because we still have a total of 180 degrees. If I know two of the angles, I can find the third one. But if we have a right triangle, we also had Pythagorean's theorem that we were able to make use of for the lengths of the sides. A squared plus b squared equals c squared. We also had the basic trig functions that we could use to solve the triangles. So our opposite, adjacent, and hypotenuse definition for the trig functions. And those work fine as long as we have a right triangle. But if we have what is called an oblique triangle, which is a fancy word for a non-right triangle, right, how do we find those missing values? How do we find the missing angles and missing sides? Now, in order to solve any triangle, and this is what we said before, we can solve it if we know the measure of at least one side and any of the other, or any two of the other measures, right? So that could be any combination of angles or sides, but we have to know at least one side. Now, depending upon what information we have these different classifications of triangles, and these are just labeled depending upon if you know angles or sides and what the relationship is between those angles and sides. So listing the different cases, we have what's called the AAS case, which is where we know two angles of the triangle and a side opposite one of those, or what I like to refer to as a non-included angle, because if you look at number 2, the ASA case, we have two angles of the triangle and the included side is known. All right, now these two cases are essentially the same, because if you know two angles of the triangle, you can find the third. And so we still have the sum of the measures of the angles, that's 180 degrees. If I know two of the three angles, I can find the third. And so now I know all three angles and one side, and then what's left to do is find the other two sides. So those are pretty much the same case. It just depends on, initially which angle or which side you know with respect to or with reference to the angles. All right. The case number 3, this is the one that gives the most problem. This is we call it the problem child with this SSA case. It's also known as the ambiguous case. This is a situation where we know two sides of the triangle and an angle opposite one of the sides, right, or one of the non-included angles is known. And the problem that you have with this situation, and we'll do a couple of examples with it, you could possibly have a triangle that you could form, or you could possibly form two triangles. It just depends upon the information, depends upon the numbers. Or there could possibly be no triangle that could be formed, right? So you have three different possibilities within this case, within this SSA case. And again, just notice the labeling. It's AAS, that's angle, angle, side. ASA is angle, side, angle, and then the SSA is side, side, angle. So if you look at the information that you're given is kind of in order around the triangle, that's where those little acronyms come from, or those abbreviations. But it's really just going to be recognizing what information you have with relationship between the angles and the sides, and that is ultimately going to dictate how you proceed to solve the triangle. And as I say, we'll have to address different cases that involve the law of sines in this section, and then cases that involve the law of cosines in the next section. There are two other cases, what's called the SAS case. This is a case where we know two sides of the triangle and an included angle. So side, angle, side. And in the last case, the fifth case, is where we know all three sides. So the SSS case, we know three sides and no angle. But do note there is no AAA case. Now, we said initially you had to know the length of at least one side. The reason that there's no AAA case, if you think back to when we talked about similar triangles. You could have triangles that have the same angle measures that could be as big or small as you wish, as you want to make them. So I can make the triangle larger or smaller and keep the angles the same. And so if I don't know the length of at least one side, then that leads to actually an infinite number of possible triangles that you could form, if we know the three angles. So there is no AAA case. You have to know at least one side. Now, for this section, the law of sines, this law, this process, we will be able to use to address those first three cases on the previous page. Right? The case where we had two angles and one side, or that ambiguous case, the SSA case, two sides and a non-included angle. The two cases on this page, 4 and 5, those require the law of cosines. So we'll have to address that in section 8.2. Now, the law of sines, what is it? Well, starting off with the triangle that we have on the left and splitting that triangle to form two right triangles. And I'm just going to look at the triangle first that's on the left, the right triangle on the left side of that one. And using our right triangle definition, we could say that the sine of A is h over b, right? Sine is opposite over hypotenuse. So the right triangle on the left side of that bigger triangle, the sine of angle A is h over b. The triangle on the right side, the right triangle on the right side of the larger triangle, the sine of angle B, again opposite over hypotenuse, in this case would be h over a. So I've got these two equations that both contain h. So what we do is we solve each of those for h. So the first one, I have h equals b times the sine of a. The one on the right, h equals a times the sine of b. And since h equals b sine a and h equals a sine b, then those can be set equal to each other. And basically that's how you solve a system. Right? I can replace h with b sine a, and I get b sine a equals a sine b, or vice versa. Then rewriting that equation, dividing both sides by sine A, dividing both sides by sine B, and you get this relationship. Right? And this is the one that we are interested in. Because what that gives you is, if you remember from algebra, you call that a proportion. I've got these two ratios or two fractions that are set equal to each other. That's called a proportion. And you can solve a proportion if you know any three of those four pieces. And that's where you can use cross multiplication, or, again, basically it's an equation that you're solving. And if I know three of the four parts of that proportion or that equation, then I can solve for the missing piece. Right? So that essentially ends up being your law of sines. So, and, just keeping in mind the labeling of the angles and the sides is purely arbitrary. So ultimately it's this ratio between the length of a side and the sine of the angle opposite that side. So the ratio of A to the value of sine of A is always equal to the ratio of B, the length of side B, to the sine of angle B. And then equal also C over sine C. So again, it's the main observation there is that these ratios are always the same. The length of a side compared to the sine of the angle opposite that side. It's always the same within that triangle. And beneath that, I just wrote them reverse, right? I flipped them. And depending on which part of the equation or which piece you're solving for, you may want to put the side on top, or you may want to put the angle on top. Again, it just depends. I'll show you some different examples where you may want to do that differently. But what you're doing in setting up this is what we call our law of sines. You're looking to set up any two of those three ratios. Right? So whether I have A and sine A equals B sine B, or if I have A over sine A equals C over sine C, right? Or B over sine B equals C over sine C, any combination of two of those ratios to form a proportion, like I have circled. And then setting up the proper proportion, knowing three of the four pieces, and then solving for the missing piece. These first couple of examples, and like I said, these are the AAS and ASA cases where you know two angles and one side. They're essentially the same case, because if you know two angles, you can find the third, and then once you have the third angle, you're left with finding the remaining two sides. Right? So for example, taking number 1, where I'm given the measure of angle A, 131 degrees, the measure of angle C, 23 degrees, the measure or length of side B to be 10. Now, if you find it helpful to just draw yourself a little reference triangle, and this is, let me actually draw one that has an obtuse angle in it, just to give yourself a reference, because remember, the labeling is purely arbitrary, so I could call this angle A, I could call this angle C, and I could call this angle B. And if that helps just to keep things organized in terms of what side or what angle then do that, right? It gives you a little visual perspective. I don't typically bother doing that. All I'm focused on is what information I know and finding the information I'm missing. And first observation here is I know 2 of the 3 angles. So finding first angle B, right? That's a straightforward, the sum of the measures of the angles is 180 degrees. So I'm just going to subtract the 131 and the 23 from the 180 that we know. And that leaves me with a measure of 26 degrees for angle B. Now I need to find the 2 missing sides. We need to find side A and we need to find side C. Now, once I have angle B, and here's going to be your tip off as far as when you can use this law of sines. Because we have to set up ratios between the length of a side and the measure or the sine of the angle opposite that side, you have to know a side and an angle opposite that side in order to use the law of sines. So if you notice in the initial problem, we knew angle A, we knew angle C, and side B. We didn't have that relationship, right? I didn't have a side and an angle opposite each other whose values I knew in order to set up one of our ratios. So that's always going to be your tip off. And going forward, because once we talk about the law of cosines, then you're going to have to make that determination as far as which process you use in a given situation, right, to solve a triangle. Do I use law of sines? Do I use law of cosines? And that just depends on the information that you have. So once I find the measure of angle B, I now know a side and an angle opposite each other. That's one of the ratios that I want to use in conjunction with one of the other pieces of information that we have to set up a proportion. So in this case, and I'm going to write this one generically the first time, but and it's like a lot of other stuff. You practice with this enough, you do enough problems with it, it'll become a pretty much a routine. It's a formula. That's what it is. And once you have the initial setup with the proportion, depending upon what information you have, what ratios you can use, it's all about then just solving the equation, solving the proportion. So it's a formula. And so you do a few of these and you'll start to see some shortcuts, maybe take some, little more efficient steps, but I'll write this one out in detail the first time, and then we'll maybe consolidate a little bit as we do the other examples. But I'm looking at, using B and sine B, because I know side B, I know angle B. I'm looking for side A. So the first proportion that I'm going to set up is going to contain the ratio whose values I know. Right? I know both of these. And I know this, or at least I know angle A. So there's only one unknown in that proportion. And so that's how you make that determination as far as which way to set this up. So I'm going to plug in what I know. I'm looking for side A. I know angle A, so I have this ratio of A over the sine of 131 degrees being equal to B, which is 10, over the sine of angle B, which we found to be 26 degrees. And then once you plug that information in, now you've just got this proportion to solve. You've got an equation. And to solve this, I'm just going to multiply both sides by the sine of 131. So that I get the length of side A, solving for A, equal to 10 times the sine of 131 over the sine of 26 degrees. And then we'll just plug that into the calculator and do an approximation. Now, as far as rounding goes with these, as far as approximations go, you could have a discussion about like significant digits and that type of thing. You'll talk about that maybe in physics or chemistry. They worry about that a lot more. I just use the values that we have in the problem as a guide. In other words, since I'm finding the length of side A, and I look at the information given in the problem, side B is a whole number, I'm just going to round to the nearest whole number. If I was given values in the initial problem to the nearest tenth, then I'm going to round to the nearest tenth. So I just kind of use that as a guide so that each of my values is rounded to the same decimal place or the same place value. So in this case, A approximately 17, if you type that or plug that into your calculator. And so there is the length of that side. And then that leaves us with finding the length of our other side, right, side C. And so in this case, I would set up the ratio. C is what I'm looking for. And notice I always like to put whatever I'm looking for goes first. I'm looking for side C, so that's what I'm going to put first. And I'm going to set up the ratio with C and sine C. And then again, I'm going to use that ratio B over sine B. Now I could actually use A over sine A now because I know what side A is. You have options there. So once you start finding some of the information, you then maybe have different choices as far as how you want to set up the ratios going forward. I like to try to use the information in the original problem as much as possible. We always talk about maximizing our accuracy. And remember, the length of side A that we found, that's an approximation. And if I then use that to approximate the length of side C, we've always said you're approximating an approximation, which means you're not as exact as you could be. So I always recommend use the information in the initial problem as much as possible just to maximize your accuracy. So again, I'm just going to plug in what we know. Now from here on out, I'm not going to bother writing this generic setup anymore. I'm just going to go straight to this next step, and I'm going to plug in the pieces that we have. So I have this ratio. I'm looking for side C. We have the measure of angle C. And then we have that equal to our ratio of B over sine B, which again is 10 over the sine of 26 degrees. So solving for C, I'll just multiply by sine of 23 degrees. And I've got C then equal to 10 times the sine of 23 degrees over the sine of 26 degrees. And we'll plug that in. We can approximate that again to the nearest whole number, and you should get 9. Now, of course, you could check all these calculations for yourself. Right? Type it in the calculator and just make sure we're getting the same values. Okay? But those are the three pieces that we're missing. We found the measure of angle B. We found the two sides, A and C, that we were missing. Number 2. So here I'm given the measure of angle A, I'm given the measure of angle B, and I'm given the length of side B. Now if you notice in this case, in the initial problem, I know a side and an angle opposite each other, right? I know side B, I know angle B, so I'm already set up to use law of sines. But I'm going to start with the third angle first. Notice again, I know two angles. Let's just start by finding the missing angle, angle C, which would be 180 minus the other two, like 25 and 100. And that'll give us the measure of angle C is what, 55 degrees. So there's our missing angle. And then finding the lengths of the two missing sides, right? Now again, we're basically in the same situation we were in with number 1. I know all three angles, I'm missing two sides. Let's set up the proportions. And in this case, like I said, I'm going to use this information that we have in the initial problem as one of my ratios. Right? Try to be as accurate as possible. So let's start with side A. So I can set up the ratio of A over sine A equal to B over sine B. Now, you may also, like I say, you start to maybe see some shortcuts that you can take in your calculations here. Just be careful. Now, always take the extra couple of seconds, set it up, make sure you have the values plugged in properly, make sure you have the proper ratios and proportions set up, just so, you try to shortcut too many things. Sometimes we'll make some mistakes with that, miss some numbers or put numbers in the wrong place. So always just take the extra couple of seconds, write it out, and then go ahead and solve it. So that gives us A then equal to 224 times the sine of 25 degrees over the sine of 100. And that'll give you approximately 96. And that would be the length of side A. Now again, notice I'm just rounding that to the nearest whole number because in the problem itself, the length of side B is to the nearest whole number, so I'm just using the same format. What's missing is side C, right, our third side. So here's my ratio involving side C over the sine of angle C, which we found earlier to be 55 degrees. And then again, I'm going to use B and side B as my other ratio to set up my proportion. So then again, multiplying in this case by sine of 55 degrees to solve for C. And I've got C equals 224 times that sine of 55 degrees over the sine of 100. And that will give you approximately 186. It reminds me to make sure your calculator is in the proper mode. I mean, when we're solving triangles, we're typically going to be dealing with degrees, so we've been working with radians a lot before when we were solving equations and all that. So make sure you do have your calculator set to degree mode. As always, check your mode, make sure the calculator is in the proper mode. Okay. I get down to where I want to get. There we go. All right, but again, essentially those two cases are the same. You know two angles, you know one side, find the third angle, and then you're using your ratios to find the two missing sides. Here's the problem child. Here is the ambiguous case. Now, I have all these different little cases laid out for you over the course of these next couple of slides. It's not critical that you have, you recognize which of those cases you're dealing with. I'm going to show you how to get around that when you're doing your calculations, and it'll really go back to things we've talked about before, knowing what we know about the measures of angles and the ranges of our functions, that kind of thing. So if you pay attention to the numbers in the problem, it's not going to be critical that you recognize which of these cases that you're dealing with. But this kind of gives you an idea of why, what happens or why it's happening. We said with this ambiguous case, if I know two sides and a non-included angle, right, the SSA case, you could possibly form one triangle, you could possibly have two triangles, or you could have no triangle. And so just running through these rather quickly, just you can look at these in more detail if you wish, but if the angle that we're missing, this angle B, or the angle B that we're given is an acute angle, look at the length of side B. Information given in the problem, it's not long enough to form a triangle. Right? So if I'm given the measure of angle B, I'm given the length of side C, and I'm given the length of side B, or that'd be an SSA, side B is not long enough to form a triangle. Right? Make it a little bit longer, and you can form a right triangle. That's only one triangle that can be formed in that situation. If you make it a little bit longer, notice you could possibly form two triangles. This case 3 that we're looking at. So until I find what angle A is, and so actually there's two possible measures for angle A. and you have to address both cases. If you lengthen the side B a little bit further, you could then form possibly one triangle. Case 4, case 5, or actually case 4 is another 2 triangle. No, it'd be a 1 triangle, because if I swing it over and it's the same as the length of side C, you wouldn't have a triangle. So 1 triangle, and in case 5, we extended the length of side B a little bit further. Again, there's only 1 possible triangle there. If the angle that we know is an obtuse angle, that actually makes things a little bit easier, because in an obtuse case, or in a case where the triangle has an obtuse angle, there's only 2 possibilities. You can either form 1 triangle or you can form no triangle. There's no way that you could form 2 triangles if I have an obtuse angle. And I have an example with that, so we'll talk about that when I do the example with an obtuse angle. But that's the situation, and it's similar to what we saw before, right? Either the side B that's opposite our angle B is not long enough to form a triangle, or it is, right? And so again, it just depends. Now, like I said, you don't have to necessarily recognize which of these cases you're dealing with. I'm going to show you how to recognize that within the problems. And so if you watch the numbers, the calculations that you have within your problem, it dictates what situation you're dealing with. So we'll start with number 1. I think I have an example pretty much of each of the cases. So given the measure of angle C at 46 degrees, length of side A and the length of side C. Now again, noticing my information presented, I know a side and angle that are opposite each other. Now here I know only 1 angle. So I'm going to start with the side and angle that I know that are opposite each other, in conjunction with knowing the length of side A. Let's start by finding angle A. So one of my ratios is going to be C and sine C, the other is going to be A and sine A. Since I'm looking for the angle first in this case, this is what I like to do. I like to put the one that I'm looking for on top. So since I'm looking for angle A, I'm going to set up the ratio of sine A over A. Let me maybe write this one generically, and then we'll plug our stuff in. Right. But it doesn't matter, which way you write the ratios, as long as you put them in the same order. So if I put the angle on top and side on the bottom, then I'm going to do that for both ratios, or vice versa as we did before. So I'm using C and sine C because that's the ratio that I know, the side and angle opposite each other, and then I'm using A and sine A because I know one of those two. Plugging in what we know, so sine A is my unknown, or angle A. So sine A over A, which is 56.2. And then I'm plugging in sine of C, 46 degrees, over C, 22.1. And of course we have units, some watch your units, if units are given for the side lengths, that kind of thing. All right. Now, solving this proportion, and I think I'm going to go this route. I'm just going to solve it normally. I'm going to multiply by 56.2. Let's solve it for sine A. Do that first. And from there, you may have a couple of different options. Just depends on how you want to do it. But I'm just solving first for sine A equals 56.2 times that sine of 46 degrees over 22.1. Keep bouncing back and forth here. Okay. Now, this next step, you kind of have an option. We can go directly to the inverse sine. I mean, this is the value for sine A. And I can do A equals the inverse sine of all of this. Okay. I usually don't do that. I prefer not to do that, and there's a reason for it. I mean, you could do it. And it'll give you, plug that into your calculator, A equals inverse sine of that whole big fraction. And it'll give you a value for angle A. I typically don't like doing it that way. Here's why. I'm going to say instead that A, our angle, equals the inverse sine of that big ugly fraction, 56.2 sine 46 degrees, etc. And I'm going to back up right here because this is not what I wanted to do. Scratch that. So I said that's what I was trying to avoid doing. So let me back this up. So like I said, that's, I'll just repeat what I said earlier. That's option number one. So I can plug that in. Or I'll do the approximation first on that value, sine of A. And if I plug that in, I get approximately 1.8293. So let's say the sine of A is approximately 1.8293. That's this value. Right? So like I said, instead of doing inverse sine of all of that, I first just plug that in to get an approximation for that. So the sine of A is approximately this. And that's what I was trying to get to. That's what I said earlier. I prefer to do it this way because look at our sine value. Right? We've seen this happen. We've discussed this many times. The range of our sine function is what? Is negative 1 to 1. That's a value that's not in the range of our sine function. So if I'm looking for an angle A whose sine is 1.8293, guess what? There is none. Right? And if there's no angle that has that sine value, then this triangle has no solution. And this is what I was alluding to earlier. If you watch the values that you get and use what we already know about the function values, about the ranges of our functions, those kind of things, you can determine whether your triangle has one, two, or no solutions just from that information. So in this case, let me get rid of that. It's bugging me. So in this case, the value that we have for our sine function is too large. There's no angle that has that sine function value, so I can't do anything further with this. This triangle has no solution. So that's one case that you're looking for. Okay. Number two. All right, so what we're given in this case, right, the length of measure of angle A, length of side A, length of side B. So again, what do I know? I know a side and an angle that are opposite each other. So again, notice there's only one angle given. So that's going to be our SSA case. I know two sides and a non-included angle. Or notice you have a side and an angle opposite each other that you know. So we're going to proceed as we did with the previous. I know A and A. I know side B. Let's start by finding angle B. Let's take the sine of angle B over B equal to the sine of angle A over A. Okay. Solve it for sine B. So I've got 42.1. So you've done a couple of these now. We kind of get into the routine of how we solve these proportions or solve these equations over 34.2. Okay. And then I said I like to go ahead and approximate this thing, the sine of B. And I've got approximately 0.8795. Okay. Now that's perfectly within our range of the sine function, right? So now we have to play the game that we were playing before in that previous section when we were solving equations. Because now I'm looking for the measures of angle B. I'm looking for angles B whose sine is 0.8795. And we know there's two of them, right? And even though with triangles, we're restricted on the interval from 0 to 180, right? Because we said the measures of our angles of a triangle always add up to 180. Even within that interval, we still have two sine values that are positive. I mean, there's quadrant 1 and quadrant 2. Where sine is positive. And since this is a positive sine value, I've got two possible angles that have that function value. All right? So now we're going to play the game we played before with our inverse function on the calculator. I know there's two angles. I know there's a quadrant 1 angle. I know there's a quadrant 2 angle. So let's start with angle B being equal to then the inverse sine of 0.8795. Right? And when you plug that into the calculator, you're going to get 61.6 degrees approximately. Okay? That's our angle in quadrant 1 that has that sine value. But there is also an angle in quadrant 2. And so just like when we were solving equations, we said, okay, you have to make sure you find all the solutions to the equation. This is the similar situation. I have to find all of the angles that would solve or satisfy that equation. Right? So there is a quadrant 1 angle, 61.6. There's also a quadrant 2 angle. So I'm going to say or B could be an angle in quadrant 2. 61.6 would be my reference angle. So we'll just take 180 minus the 61.6 to give us our second angle of 118.4. And so in this case, I've got two possible measures for angle B. It could be 61.6 degrees. It could be 118.4 degrees. Okay? Now, here's the other thing you want to watch. Because even though there are two angles that have that function value, the sine of 0.8795, doesn't necessarily mean that both angles are valid or viable. In other words, I already know one angle of this triangle is 45.6 degrees. Now, this angle is always going to be good. This acute angle that you get, that's always going to be a possible angle. The question is going to be about this one. If B is 118.4 degrees, the question would be, is my triangle, do I have enough room in the triangle for that angle? Well, being that we have already 45.6, there's certainly plenty of room in the triangle for 118.4 degrees and still have room left over for a third angle before I get to 180 degrees. I'll show you an example of one next where that doesn't happen, right? So kind of what you're watching for. But, the first angle is always a valid angle. The second angle, do I have enough room in the triangle to have that second angle and still have room for a third angle? Right? And I'll show you what I mean with the next example. But in this case, we do. So if that's the case, well, guess what? You've got to give solutions for both triangles. So I'm going to say here that there are two possible triangles because there are two different possible values for angle B. And that's why I told you earlier, that's why we call this case the problem child, this ambiguous case, this SSA case. So now I've got to deal with both of them. So let's just say the first triangle, if we take angle B, is 61.6 degrees, and so then we'll go through as we did before. Now with that second angle B, we can find angle C. So I could tell you that angle C, then let's say C would be 180 minus the 45.6, which was angle A that we were given in the problem. So minus the 61.6 for angle B that we're given, or that we found. And that gives me the measure of angle C at 72.8 degrees. So now I've got all three angles. The only thing missing is side C, because we were given side A and side B in the initial problem. So now we're going to find side C. And since I'm looking for side C, I'm going to use C over sine C. The sine of angle C that we just found, equal to a ratio set up with one of the other two, either A sine A or B sine B. And since I know A and angle A in the initial problem, I'm going to use A over sine A. As I always like to use the information in the initial problem as much as possible, just to maximize the accuracy. So I'm going to set that up to or equal to the ratio of 34.2 over the sine of 45.6 degrees. All right, so that's our A over sine A from the initial problem. Okay. And we'll solve it for C. So that gives me C equal to 34.2 sine of 72.8 degrees over the sine of 45.6 degrees. All right, now that's the length of side C, so I'm just going to go ahead and plug that in, and I get 45.7. And that would be the length of side C. Okay. Now again, that's just our first triangle. And so I found angle C and now side C. Those are our three pieces, B, C, and C. So then we have to address the second triangle. Because we said the other possible measure for angle B was 118.4 degrees. So if B is 118.4, then we'll find angle C using that measure for angle B. So that would still be 180 minus 45.6, which is angle A, but then now using 118.4 for angle B. And this is what I was saying earlier. So notice I can subtract this out, and I'm left with 16 degrees. So there's room enough for angle C in my triangle. If I subtracted those from 180, and like a negative number, I guess, if I can't take away more than what I have, then that would tell me that I would not have enough room for that third angle, right? So there would be no angle C, so there would be no second possible triangle. And then again, now that we have angle C, we'll find side C. Well, let's just use the same setup we have earlier, in that what C would be equal to, because all we did was change the angle C that we had, so from 72.8 degrees above to 16 degrees here. So I'm just going to replace that angle in our calculation. So 34.2 sine of 16 degrees over our sine of 45.6. And that'll give you approximately 13.2. as the length of side C. Right? And so yeah, I mean there you go. It's the problem with this case, that if you have an SSA case, you can possibly have two different triangles coming from that. Yeah, that's all I'm going to. All right, so number 3. So we kind of had the first two cases. The first one where there was no triangle. The second one where there were two triangles. What about a case where there's only one triangle? How do I recognize that? Well, first of all, the fact that this triangle has an obtuse angle, right? Angle A is 126.5 degrees. I know right there that there could at most be one triangle. There's no way you can have two different possible triangles if one of my angles is an obtuse angle, right? So we know there's only possibly one. Now, there still could possibly be none, right? It doesn't guarantee I have a triangle. I could still possibly have no triangle. So the first piece of information I'm going to find, knowing angle A and side A, and knowing side C, let's find angle C. Okay. So angle C, take the ratio of the sine of C to C, and then setting that equal to the sine of A over A. So again, we're using one of the ratios where we know both pieces, A and sine A, or A and angle A. And then we're setting up the other ratio depending on which piece we know. We know side C. Let's find angle C. So solving for sine C, that gives me the sine of C equal to 13.5 times the sine of 126.5 over 17.2. And that will give you approximately 0.6309. But notice again, I mean, that's the sine of angle C. It's a positive value. So there are two angles with that sine value, right? There is a quadrant 1 and quadrant 2 angle because the sine value is positive. Okay, so we have to take that in consideration. Now again, we already know that there's only going to be one possible solution here because of that obtuse angle, but I'll show you how I know from the numbers. Right? So let's go with C equals inverse sine. Let's find first that acute angle, 0.6309. And that'll give you an angle of approximately 39.1 degrees. And notice again too, I haven't emphasized it going through these different problems. And I said rounding, what place value do I round to? Well, notice the information in the problem that we're given. The angle is to the nearest tenth, the side is to the nearest tenth. So I'm rounding to the nearest tenth. I'm just going to be consistent with the values that are given in the problem. Okay? So we'll round everything to the nearest to the same place value, or at least all the angles to the same place value, all the sides to the same place value. Okay? Well, there's angle C. Now, we said there could possibly be a second angle, right? Because there is a quadrant 2 angle as well. So let's say or, put it right here. C technically could equal 180 minus that 39.1. But 180 minus 39.1 leaves me with 140.9. Okay. And if I have then an angle of 140.9 for angle C, there's no way that can happen because angle A is already 126.5 degrees. Right. I don't have room for this big angle in my triangle. And it doesn't happen with just the obtuse angles. It can happen if the angle is acute as well. But that's what I mean by when you find your angle, your second angle, do you have enough room in your triangle for a third angle? And in this case, definitely we don't. We don't even have enough room for the second angle, much less a third angle. So there's only one possible triangle here. And that's where angle C measures 31 or 39.1 degrees. Okay? So then what do we need? We need side B. We need angle B. Well, now that I have angle C, let's go with angle B. Once I find that second angle, then I can find my third angle, right? So B would be 180 minus the other two, 126.5 for angle A, and 39.1 for C. Right. And that leaves us with, what, 14.4 degrees. For angle B. And that then just leaves side B. Okay. Now that I know angle B, we'll go ahead and set up our ratio. B to sine of B, which is 14.4. And then setting that equal to, again, I'm going to use the original ratio from the original problem, A and sine A, so 17.2 over that sine of 126.5. 0.5. I could use C and C if I wish, but I'm using A and A from the original problem. We'll solve that for B. So B would then be equal to 17.2 times the sine of 14.4 degrees over the sine of 126.5 degrees. And that would give you approximately 5.3 for the length of side B. Okay. Yeah, so that's the SSA case. That's the tough one. You have to be careful there. And I said, if you watch the numbers as you are doing the calculations, it'll tell you how many possible angles can be formed or you could have, and then how many possible triangles, whether it's 0, 1, or 2. All right, so all of those are just kind of, generic little triangles. Of course, at some point, we put that in the context of an application. And so we have applications where these triangles pop up, and we're solving applications as we did before. But the advantage from previous was we had right triangles. And we always said that when we were drawing our diagrams. We kept saying, well, we're at the advantage in that we know that we have right triangles somewhere in my diagram, and that was helpful. We don't have that anymore. And this is as straightforward as the solving of the triangle is, because it will be. And you practice enough with those, what we just got through doing with solving triangles, that's pretty straightforward business. As long as you know the formulas, as long as you recognize how to set it up, that's pretty straightforward business. This is, as always, what gives most of the problem. All right, the application problems, I know a lot of us struggle with it, but it is what it is. I mean, it's the more useful part of this. I can actually use or make use of this information in kind of a quote-unquote real-world application. And so do a couple of those. But when we talked about applications previously, we kept saying it's all about the diagram. You've got to be able to sketch out the situation, draw the diagram, and once you have the diagram, then you're back to solving the triangle. But you've got to get the diagram first and foremost. So I'm looking at number 4. I've got an airplane leaving an airport on the east coast of the United States, flies in a direction of 85 degrees. Because of bad weather, it returns to another airport 230 kilometers due north of its home base. To get to the new airport, it flies in a direction of 283 degrees. What is the total distance the airplane flew? All right, so now this is one of those bearing type problems because we're given direction strictly in degrees. I mean, when we're measuring direction given that degree, then our angle is measured from due north. I mean, we had the two different types of bearing. So this was that bearing where we were measuring the angle from due north at 0 degrees and then measuring the angle clockwise from due north. Right? So the airplane leaves an airport on the east coast of the United States and flies in the direction of 85 degrees. So here's our airport. Flies in a direction of 85 degrees. So that's that angle being measured from due north. And then we said at some point it had to turn around and head back to a different airport because of bad weather. The second airport, we're told, was 230 kilometers due north of the original. So that's what then I'm calling airport B. We said the heading of the plane to that second airport was 283 degrees. So again, from this point, from point C out here, from due north, we're measuring 283 degrees. And that should be this one, actually. Okay. All right. And we're asked for the total distance that the plane flew. So I have those angles labeled ABC. The angle labeling is arbitrary. Label whatever you want. Just keep track of what's what. So that would make this side A. That would make this side B, and that would be side C, the one that we already know. Okay? Okay. Trying to think. Yeah, we're good. Okay. I was just double checking something. All right, so yeah, there's our triangle. And so essentially what we're doing is we're looking for side A and side B of our triangle. Now, what do I know? Well, at least I know angle A in my triangle, but I know that, and I know side C. I need a third piece of information. I think we can figure this one out. I can figure out this angle C because we have that 283 degrees. I know this is 180. What's the measure of this angle? It's 85 degrees. That's one of those transversal type problems. Remember, we have the two parallel lines and then the transversal, which is side B. And so whatever the measure of this angle is, has to be the same as the measure of this angle. So that's a transversal running through those parallel sides. And since that's 85 degrees, and I already know the 180, I can find the measure of angle C within our triangle. Right? But we keep saying with this stuff, it's all about the diagram. You've got to be able to draw the diagram reasonably so that you can find that information. So I'm just going to say that angle C, and the angle C I'm referring to is the angle in our triangle, would be that 283 degrees minus the 180, and then minus that 85-degree angle that we found. And that'll leave us with, 18 degrees. That's the measure of angle C. Now, also you may find this helpful as well. And we said before with diagrams, especially now, we're going to have a lot more. The diagrams are going to be a little more complicated than what they were before with our right triangles. Once I get the information I need, I always like to maybe pull my triangle out and just put everything clearly in terms of what I know about the triangle. So this is angle A, this is angle B. We're calling this angle C. We know this is 230. We know this is 85. And we found angle C to be 18 degrees. Because now once you do that, now we're just back to solving the triangle. Now we're back to doing what we were just doing, finding the length of side A and side B. Okay. So I can start with side A. Or I'll tell you what, let's come down here and I'll say, what do I know? I know the measure of angle A. I know the measure of angle C. And I know the length of side C, because that's what this guy is. And we need to find the lengths of the other two sides. Right? What's the length of side A, and what's the length of side B? Okay. So we have one ratio that we can set up. We have C and C. So let's start with A. I'm going to go A over sine A equals C over sine C, which means A then would be equal to 230 sine of 85 over the sine of 18 . And that gives you approximately 741. I'm just going to go to the nearest whole number because that's what the other side is, the 230. So I'm going to go 741. Remember, our units there is kilometers. So that would be the length of side A. And then we'll find the length of side B. And first of all, I can find angle B. which would be 180 minus the other 2. And for angle B, that leaves me with, what, 77 degrees? Let me box this because that's one piece of information that we need. That's A. And now with angle B, I can find the length of side B. So now we've got our ratio of B to sine B. And again, I'm just going to use the 230 over sine 18, the C over sine C. So that B would be equal to 230 sine of 77 over the sine of 18. And that'll give us approximately 725 kilometers. And that's side B. All right, and our question was, what was the total distance that the plane flew? So that's the distance flown along side A going out, alongside B coming back, or vice versa, side B going out, side A coming back. But our total distance, of course, we just add the 2. So this is what we're asked for. Total distance would be the 741 plus the 725. And that gives us, what, 1466. 1,466 kilometers. Total distance traveled. Okay. A typical application, I mean, very similar to applications we dealt with back early on with right triangles. The big difference, though, we don't have a right triangle to fall back on. Right. So watch, you review back the heading, the way that we measure heading. In this case, it was strictly in degrees, which is measured from due north clockwise. And then those transversals, right, passing through the parallel lines, and how I can use that to get angle measures. The next one. A boat leaves Lighthouse A and sails 5.1 kilometers. At this time, it is sighted from Lighthouse B, which is 7.2 kilometers west of Lighthouse A. We're given the bearing of the boat from Lighthouse B to be north 65.2 degrees east. Right? I went ahead and converted that DMS to just strictly decimal degrees, so north 65.2 degrees. How far is the boat from Lighthouse B? Right. So what are we given? We're given 2 lighthouses, Lighthouse A, Lighthouse B. We know that Lighthouse B is 7.2 kilometers west of Lighthouse A. B is 7.2 kilometers west of Lighthouse A. We're also told that the boat left Lighthouse A, or was sighted from Lighthouse A, and sails 5.1 kilometers, but we're not given a direction, right? So even though we sailed in 5.1, we have the distance that the boat sailed, we're not given a direction. We're not told in which direction it left from Lighthouse A. Now, we are given a bearing from Lighthouse B. We're told that the boat was sighted from Lighthouse B on a bearing of north 65.2 degrees east. That was that other type of bearing that we had, north 65.2 degrees east. So we start from Lighthouse B, we measure north, and then 65.2 degrees east of that north-south line. And that's the line of sight from Lighthouse B to the boat, which I have marked at C. Lighthouse A, Lighthouse B, and then C is our boat. Now again, I don't know the direction that we went from Lighthouse A, so I just drew in a line that was 5.1 kilometers, or represents that distance, but I don't know the direction. Okay? So that maybe kind of leaves us, notice we're dealing with a triangle where I know two sides, I think we can figure out this angle, angle B. And that's going to be one of those SSA cases, right? Unfortunately. So if you kind of look at just from the information that we're given or lack thereof, the fact I don't know what angle A is, I don't know the direction that the boat was sailing. Yeah, that opens up a lot of different possibilities. So let's run the numbers. I mean, if I don't recognize that, no big deal. Run the numbers and see what comes out of it. So I can start by first finding angle B. That's not a problem. Because we know that this angle here has to be a right angle, because that's a straight east-west line and a straight north-south line. So that has to be a right angle. So I can tell you that angle B would have to be 90 degrees minus the 65.2 degrees that we have. That'll give us 24.8 degrees as the measure of angle B in our triangle. Okay. Now that sets us up with an SSA. So I'm going to go ahead and pop that in right here, 24.8 degrees for angle B. All right. And our question was what? How far is the boat from Lighthouse B? So I'm looking for that side, which would be side A. Right? How far is the boat from Lighthouse B? Okay. Well, what do we know? We know, I'm going to go ahead and call this side B. I'm going to go ahead and call this side C. So we know angle B and side B. We know side C. Now I'm looking for side A. I don't have information I can use yet to get A, because all I know is the length of side C. So I can set up a ratio, but I'm going to have to first find angle C so that I could then find angle A, and then we can get around to setting up the ratio that we need to find side A. All right. So first, angle C. Scratch that. Let's go C over sine C. Put it that way. I don't think what I want. Oh, that's what I wanted to write. Find C. I'll write what I say. All right. So finding C. Setting up our ratio with C and sine C. So I'm looking for angle C. So how about sine C over C equals sine B over B. And then we'll solve it for sine C. Equals 7.2 sine 24.8. Get out of my way. Over 5.1. And as I did before, I'm going to go and approximate that first. I get 0.5922. As the sine of C. So then we'll take C to be the inverse sine of 0.5922. Plug that in and we get approximately 36.3 degrees, or, because again, that's a positive sine value, there's a Q1 angle and there's a Q2 angle. Because that's our ambiguous case, 143.7. And the fact that the only other angle in our triangle is 24.8 degrees, 143.7. I still have room for a third angle out of 180 degrees. So yeah, unfortunately, that's what we suspected from the original problem, because we didn't have a direction of the boat from lighthouse A. I didn't know what angle A was. We have two different possible triangles that can be formed out of this. Okay. So we'll address each case. So I'm going to say two possible solutions. Okay. So first, if we take angle C to be 36.3 degrees, because remember why we were finding angle C? So that we could find angle A. And then we could set up our ratio to find the length of side A. So if C is 36.3, then A in that case would be 180 minus our 24.8, which was angle B, minus this 36.3. And that would give me a length of, or measure of angle A at 118.9 degrees. And then we can set up our proportion. Right? So then I've got A over sine A, and I'm going to use B and sine B. So side A, which is the one we're looking for, that's our distance from lighthouse B to the boat. So I've got A over the sine of A equal to, and I'm going to use B and sine B. That's the sided angle opposite each other that I know. So 5.1 over the sine of 24.8. So that'll give me A equal to 5.1 sine of 118.9 over the sine of 24.8 degrees. Come back. And that gives me approximately 10.6, and that's the length of side A. Our distance there was given in kilometers. So that's one possible distance. Or secondly, if C, we chose C as the other angle, 143.7. Then in that case, our angle A would be 180 minus the 24.8 from angle B, minus this angle C of 143.7. And that would give us an angle A of 11.5 degrees, approximately. Okay. Then, let's say we'll just change our angle there. So I have A equal to 5.1, and then just replacing our angle from 118.9 to 11.5. degrees over the sine of 24.8. Right. So all I did was just change my angle here with the new angle A. And that would give us a distance of approximately 2.4 kilometers. Right? So yeah, it's a pain, right? It's a bit of work with these ambiguous cases, with the SSA case, but you've got to be on the watch for it. Unfortunately, it's part of the deal. Right? All right, so that's solving the triangles. Okay. The last little piece of this section, I'm not going to do a whole lot with this. It's another formula. Area of a triangle. You know, I mean, you have formulas for finding it, or a formula for finding the area of a triangle that you've probably known from elementary school. Right? The area of a triangle is 1/2 times the base times the height. And that's the formula that you're taught from when you're knee high. Right? Well, this is just a variation of that, but in terms of our trig functions. So here's our 1/2 base times height, using the letter K to represent the area. For whatever reason, we're using K. Makes perfect sense, K for area. Here's our triangle, triangle ABC. Now I've drawn in a height for that triangle, right, perpendicular to what we could call the base of the triangle. So if this then is the base of our triangle, and then the height is measured perpendicular to the base. So whichever one you measure the height from, that's the side that's called the base. So our base in this case is side A. So if we take that 1/2 base times the height, since I have a right triangle there, if I look at the sine of angle B with respect to the right triangle, sine of B can be defined as H over C. Or I could then say H is C sine B. And again, I'm just looking at this right triangle. Right. Okay. So sine of B is H over C, and then just rewriting that, I have H equals C sine B. So H is the height, right? So we take our formula 1/2 times base times height, where the base is side A, because that's the side we measured the height from. And now I'm replacing the height with C sine B. And you get this formula then that the area of the triangle can be found using 1/2 times AC sine B, or generically, the area of triangle ABC is half the product of the lengths of two sides and the sine of the included angle. Because notice angle B is the angle that's included right between those two sides, A and C. And so again, just generically, any two sides and the angle included between those two. So 1/2 BC sine A, 1/2 AB sine C, 1/2 AC sine B, all arbitrary, just depending on how the sides are labeled. But it's two sides and the angle between the two sides. Right? So that gives us a pretty straightforward little formula. Now, obviously, and this is always what happens, so I'm going to caution you, and I'll caution you, and I'll caution you. You've got this law of sines that we're talking about for finding the sides and angles of the triangle. That's a formula. You have this now area formula for finding the area of a triangle. What information do I have to do that? Two sides and an included angle. Then we're going to go into section 8.2 where we talk about the law of cosines. There's going to be more formulas, those involving cosine. Don't get them confused. How many times do I see, especially with this area one, cosine used here instead of sine? All right, so keep them straight. You gotta, what formula, what function gets plugged into which formula. I see way too many mistakes with that, and you just got to know. I mean, there are formulas. It's about as straightforward as you're going to get. You're just using a formula, plugging numbers in, but you have to know the formulas. Okay. So we're just going to do one little quick example with this one. I think so. I'm not going to do a whole bunch with this. So finding the area of the triangle, given the measure of angle A, the length of side B, the length of side C. But notice those are two sides and the included angle. Right? You can always recognize the side and angle opposite each other because they have the same letter. So if I have sides B and C and angle A has to be between sides B and C. Right? But otherwise, like I said, just a straightforward formula. Nothing more to it than this. So we'll say the area of the triangle is 1/2 the product of those two sides and the sine of the angle between the two sides. Right? And we'll just plug in our values. So I've got 1/2. B is 10, C is 13. and the sine of the included angle, angle A of 17 degrees. And if you plug that in, you will get approximately 19. Watch your units. Remember, this is area, so units are square feet, right? Okay. Now, you may have an application that pops up in your homework in dealing with the area. That's fine. I mean, find the area of a region. Just make sure the information I plug in are two sides and the included angle. Okay? That is section 8.1. All right, section 8.2, we'll talk about law of sines. See you then.